Ooh, so excited. Everybody is so excited. And the AI rage is here. If I can say it, call it that. Everybody is so crazy about AI, Gen AI, LLMs, all of that. And we are all trying to catch up, but every day there is one thing or the other coming up. So in this event, the idea or goal is, of course, to build AI agents or at least get this gist of what it is, why it is so popular, and all of that. Thereby, when you go back to your work, you can start implementing some of these patterns. So the focus is more on understanding these patterns than building a full-fledged production-based application. Uh, to really bring the expertise for today, I have brought Maurish Dev from ThoughtWorks. He has been internally advocating a lot for AI agents and has been propagating what software engineering looks for building AI agents. So I want to quickly hand over the mic to Maurish Dev and get started with this rave. Um, Usually we will say, give a big hand for our speaker, but here you can give an emotion or emoticons to welcome our speaker onto the stage. I'm going to stop sharing and hand it over to Maurish. Welcome, Maurish.
Hi, Bhavani.
Bro,
Thanks for
अभी
the.
bro react करो ना.
I'm going to ask everybody to mute yourself. Just be conscious of that. Thank you. Maurish, you can take over.
Thank you. Yeah, so thanks, Bhavani, for the introduction. And hi, everyone. This is Maurish. So I'm working in corporate as a software engineer, and I have been meddling with LLMs and AI for a while. From the perspective of software engineering, that is to understand, yeah, that is to understand more on like what AI or LLM spaces, how to structure them in a way in software engineering. Right now, it's all completely bloated, and any we can define LLMs in any way that I want, that we want, right? And coming into agents, right? So there is no particular structure of what is an agent, what is not an agent, and what is a workflow, what is an LLM applications. There are a lot of jargons around going on around there. So I am here to break that jargon down. So we'll deep dive into the complete basics of agents, like why we need an agent and all those stuffs in this session. So I think everyone is ready for that, and this will be a theory for a while. So um, then we'll get into the hands-on sessions of that. So that being said, I think we quickly start onto the session. I hope you have the link to the GitHub project that was shared earlier, right? So in order to move to MCP agents, I think everyone would have been excited about MCP and building agents. So even before that, we wanted to understand and what agents are. So for the first 30 minutes or 40 minutes, we'll deep dive into the theory part of it on defining an agent. So we'll get to understand more about what agentic approach and agents, agentic RAG. So all these things, what are they? So we'll be breaking them down and in a way that even a non-tech person can understand. So agents came into the picture, right? So what is an AA agent? In order to understand what is an AA agent, we wanted to first explore what LLM large language model is, what is the practical shortcoming of a large language model is. So that actually paved the way for the need for actually the AI agent. So in order to understand what is a practical shortcoming of an LLM, meaning what are the limitations of LLM, we wanted to understand what actually a large language model is. Okay. So at any point, disclaimer, at any point of time, if you feel like having a conversation, it's not a presentation, it's a conversation. So feel free to pitch in at any point of time. You can unmute, speak, you can put your questions on chat, you can converse on chat. Right? Yes. Okay. Feel free to do that. So with that being said, large language model, right? So large language model are nothing but like it contains a large set of data as an input. That is already it, right? So what you do with the current ChatGPT or Claude or Gemini, so what do? So you ask some questions and it gives you some answer, right? From a normal people's perspective, right? But that perspective has to change because these large language models are nothing but designed in a way in order to complete your question or complete your sentence. It's a text completion tool, large language model. So it does not try to answer your question, but it tries to complete the sentence that you have given to it. That is nothing but a large language model. So that is what the pictorial representation, visual representation I've showed in here. So the input that is given to a large language model is Romeo and Juliet is a tragedy. Okay. So it tries to complete the form the next word using the previous words altogether. Romeo and Juliet is a tragedy. The next probable word that can appear in the sequence is return. Okay. Same way, it tries to form all these words. So now you'll have like much more questions on what this auto generation is, what is probable words is. So let's deep dive a little more into that, right? So how this large language model came into existence, right? So we have like machine learning before, and what is the difference between machine learning and large language models, right? So there will be a lot of questions
Hey,
around.
Morish. Sorry,
Yes,
one quick question before going
sure,
further.
sure.
I see Google has been doing this search, how do I say, prediction since a lot of time. It's not new. So why didn't we call that time it's a large language model, and why are we calling now it as a large language model when, especially when it comes to ChatGPT or some other chatbots?
Got it. That is primarily on machine learning. So machine learning in a way that it does not have contextual understanding of the text that you throw in. So that was what Google was doing it earlier. For example, like 5 to 10 years, 5 years back, if you had used the Google Translate, right? The Google Translate, so the sequence of words that you put in English would be different when you're using in French, right? When you say, how are you? So it won't be how are you. It would be like in French, it would have changed it to are how you, right? But now, if you ask the Google right now, Google Translate, how are you? It correctly understands the context on how are you, and it tries to match the exact sequence of words in other language. So this is the exact difference between machine learning and large language model that you put into. So large language model came into existence because it is trying to preserve the context of the input that you are giving into. Okay. So that is why we have been calling this as a large language model and not a machine learning model altogether.
Cool. That's a nice example. Thank you.
Perfect. So little deep dive into it. Large language model has a much more different components, but we'll first break down the jargons that we have in the large language model. Okay. First thing is machine learning models trained on large corpus of data, and this has to, like when you say large corpus of data, let's say in the sequence. In this sequence, if you see, Romeo and Juliet is a tragedy written by William. So how does this large language model or machine learning model tries to get the next word as Shakespeare? So it can be William Johnson, can be William anything, right? So how is it able to get the name of Shakespeare? Right? So this is where the contextual meaning or representation comes into the picture. Now, when you train with a large corpus of data, you would have this information also into that particular data, right? Stating that when you talk about Romeo Juliet is a tragedy written by, so the model would try to understand that you're referring to a Romeo and Juliet story, and the story was written by William Shakespeare, and I know this data prior to it. So that is nothing but training your model to understand the context that is being given. Okay. So training, context, model. So this is what is revolving around large language models altogether. Okay. This again started with your natural language processing, right? So coming back to the same example that I've given before. So you give an text in English and you wanted to convert it into French, but at the same time you want to preserve the context that you are giving. So how are you should be how are you in French, not you are how. So that completely breaks down the context altogether, right? So what next researchers developed is something called as, after machine learning model came to the picture, now LLM why comes into the picture is, so they have built something called as, you can just note down these jargons. So I'll just decode it in a way that you can understand it, but there are much more to it. So I break down few jargons of it that we are going to see today. Okay. So transformers. So what do you know transformer? You basic is you transform something, right? So that is nothing but you give an input, you get something as output. That is the gist of transformer. Now, what happens inside the hood in a large language model? What it does is they have built two different components inside transformers. That is encoders and decoders. Okay. So what does this encoders do? Right? So when you put in an input text, this is where the large corpus of data that I mentioned before comes into the picture. Now, you provide this large corpus of data into the encoder. Now, this encoder uh, tries to convert this large corpus of data, that is, break down the entire large corpus of data into numbers that this particular machine can understand, and saves it into its knowledge base, and at the same time preserving the context. So how does it preserve the context? It uses something called as attention mechanism. Okay. So attention mechanism is something like, I'll not deep dive into attention mechanisms or anything, but I wanted to get you to understand the feel of what happens inside the hood of large language models. Okay. So you input a text, how are you? So it tries to learn from that particular text. It converts that text into something called as tokens. Okay, so in LLM world, uh, what you call as words in English or text in your input prompt or anything, right? To large language model, those are called tokens. Tokens are fundamental building blocks of a large language model. Okay, so when you give words into the encoders, now this encoder, what it does is it preserves the contextual representation of the data that you are giving it. That is, when you provide like jaguar is an animal, okay.
Sorry.
And my favorite, yes.
Is letter a token or is a word a token when we reply?
So got your understanding. So here, the tokens or nothing, or it is not a letter nor a word. It is something, chunk of data, breakable data. When you given your exactly what the input is, nothing but the words. But the words are not the tokens. It is something, a breakable chunk of data by a model that it can be converted into its representation that it can understand. So it can be converted, which can be converted into numbers that that particular model can understand. So for each and every model, there will be different way a token can be represented. Like for example, when I say, how are you? Can be, how is a one token. It can be like HO can be one token for a model. WAR can be another token for a model. So it is not exactly words that is equivalent to a model. Sorry, equivalent to a token. Sorry. Yeah,
So basically, it depends on the LLM itself, how
exactly.
it would yeah, basically divide the words. Okay,
Yes.
thanks.
So I'll show you how different models, like convert, represent these tokens in their for their use case, right? So there's a beautiful UI. So I'll show that after explaining this. Yeah, remind me if I move to another topic and don't show that. Okay, cool. Uh, Coming back to this encoders, right? So it converts into the tokens that it can understand and saves it in its own knowledge base, so that if this particular decoder, okay, so if that particular decoder asks for it, it checks in the encoded data, what it is. What is the large corpus of data that is it has in its input, and tries to give a response. Okay, so this might be a little confusing for you on the decoders part, but on the encoders part, do you have any other questions or anything that you don't understand? So that because this is the most important part in a large language model that goes into. Now, what we'll do is we'll take all these things out of the picture. Attention mechanism. Now, you have converted your entire large corpus of data into a knowledge base and stored in the model. Let's call that as an OpenAI model. So now what you have done is you have created an OpenAI model altogether. Now we have to use that model. Yes, this is where you remove this. You have your decoder. Now this transformer is nothing but becomes your GPT. What is a GPT again? Generative pre-trained transformer. So you have already trained your model using an encoder based transformer. That is nothing but your pre-trained transformer. I'll come to the generative part of it next. And when you give a chat or a text interface to this GPT, that becomes your chat GPT. Welcome to the chat GPT world. And this is what chat GPT does. Okay. So now I'll come to the decoders part of it. And that is where the third point comes into the picture. So all,
There is a
yes.
question from Aditya.
Yeah. Hey, thanks. Once the GPT is formed, since we also see the models get trained again on the outputs that it produces, just curious, would there be an encoder again that pushes the GPT generated data back to the model, or how does the output goes back to training?
So when you say output goes back to training, it actually doesn't go back to the training because it is already. Aditya, can you come back on the question? I was not able to understand the question very clearly.
Yeah, I meant so we are training the model via data via the encoders, right? And once it comes as a GPT form, it also produces it produces outputs, generates code and is customized based on human taste. So does the output produced by the GPT goes back to the model again by encoding back, or how does it hold how do I put it, maybe is there someone who can help?
Got it. Yeah, I got the picture. Now again, you give a text input prompt to it,
Right.
and there's output that coming out of it. And how does that output? Is it again going back to an encoder model, something like that?
Right. Because it would have seen a lot of human taste on what humans want. Right?
Got it. To answer your question in one word, one sentence, actually the way that this is where I'm coming to the next part of it. Maybe I can explain this regressive of a large language model so that you'll be able to understand it better.
Sure.
Yeah. If it doesn't answer the question yet again, do let me know.
Cool.
Okay. So the third jargon in a large language model in a decoder styled transformer, that is nothing but a pre-trained GPT, right? So this is nothing but a decoder based transformer, decoder only model. Okay. So what it does is it generates a response auto-regressively. That is, it continues to complete your sentence or your text in an auto-regressive manner. So I think many of you would have heard on regression testing. What does a regression testing mean? So you have an existing feature altogether, something new comes in. So you have an existing feature altogether and something new comes in, and what you do is you test the old feature as well as the new feature and ensure that none of the new feature actually is breaking the existing working of it. So we'll take the testing part out of it, but the regression means that in here, so you give the old data into it and you generate a new data altogether. So that is nothing but a regression. That in LLM, how it does is, take this decoder alone. So I have this whole text as, how are you doing? So how does the chat GPT now works when you give this particular prompt? That is, how does the auto regression works? So at first instance, what happens is, how are you, the entire text goes into your decoder, right? And now decoder is already having that large corpus of data, which is preserving the contextual representation also. Not just the data, but also preserving the context related to a particular conversation. Okay. So now this how are you doing comes into the decoder. Now this decoder reads the entire data. Now the data is converted into tokens. Now there is no encoder comes into the picture. Now it's only the decoder which does the job for you. How are you doing converts it into tokens. Right? So I'll put a pass in here. I told that how tokens would represent in different large language model, right? I'll show the tokens so that it will be easier for you to understand what is the difference between the words and tokens. Okay. There is a beautiful UI was developed. I'll share it in the Zoom link as well. Okay. So this is for ChatGPT 4.0. So as far as you can see, let's say that how are you doing? So in here, each and every word is converted into a token. In this context, since it's a very small chunk of word, so it is able to divide that into each, and the tokens would be each and every word. What if I do this? I am a large. So when I have specified like I'm a large language, now this I'm a large language is converted into tokens in such a way. I is one token. AMAL is another token to the decoder model, large language model. Okay. ARG, this is another token to it. So it is not exactly converting into word by word, but it is converted into a way that that particular model can be used, can use this as a token for its input. Okay. So that depends upon each and different models altogether. Google Gemma can use it in a different way. So in here, if you see in GPT 4.0, I was a token, but in Google Gemma, IAM is one single token. Right? So just like different languages, meaning normal Google, English, French, different languages, even large language model have different ways of representing its tokens or its words. The numbers actually, Vishwan. Kirtivasan, I'll come to you. There's one question in the two questions in the chat. What does that color coding represent? The color coding is just a textual representation of different, different tokens. So in order to represent IAM is one token. So it shows like in different color coding just for textual visual representation of tokens. I think that answers the question. Abhishek, if not, let me know. What does the numbers represent? Numbers represent, it actually represents something called as like weights. in self-attention mechanism, weights or nothing, but you give a random number based on your attention details. So I'll not get deep dive into these numbers. Just think of these numbers represent something in a coordinates. Okay, so you have an XY graph. You have I am a. So each and every token represents some space in your graph altogether or in your XY axis.
If I may interject for 1 second,
Sure.
neural networks are mathematical statistical models. So if you give it English word, it cannot understand. So anything at every layer that you do, you have to convert that into numbers. And that's what these numbers are. These don't have any inherent meaning for the human eyes. But for a machine learning model, if you put cat and dog together, it will have very similar numbers, meaning that both are animals in a huge, large space. If you put king and queen together, it will have a very similar name. And until before large language model became a thing, because it has a lot of data, a river bank and a money bank will be conflicting with each other. So we had very interesting word vector problems. These are called word to vectors. So that's what these numbers are. Inherently, at the fundamental chip level, everything is numbers. So you have to convert your words also to numbers. That's what these are.
Yeah, thanks for that crisp and clear explanation, Bhavani. Yes. So I think that clears your question, Vishwan. And I think Kirti wasn't raised his hands, right? Yeah, you can go.
Yeah, Maurice. Thank you for that. The word is basically being as you said, the token is not representing a word, so it just splits up. So if this text itself is ripped up into different sections, so how does this help in forming a word or correlate to other stuff? Maybe that's something that you're coming up in the explanation, but still curious answer. Good question. Like you are like ANG UAG, so I think that takes up a different token, right? So how does that help in if you ask me language, okay, that's a word, okay, that's gonna help in bringing up a sentence or making a clue or something like that. But how does breaking up the word totally and putting it as a token, how does, like, is it not making it more complex for the LLM? Yeah, that was my question.
Got it. Got it. Yes, this neural network is completely complex, and this only can a neural network model or a machine learning model can understand, right? So this is how this particular data has been trained on. Okay. So when you break it into chunks, right? So now you have to think from a perspective of a not a normal word, like when you understand I am a large language, right? So the next word should be model. We know that it would be model. Our brain can represent it. Now, how does the machine can represent it is it's not a direct conversion of, let's say, large to some number in their data, because we don't know how their data would be trained on, right? So this is how they have been trained on. So when you only can break the tokens like this and convert it into the numbers or the numerical representations, so it can then only able to identify that the next probable word in the sequence can be model and still adhering to the context of this particular sentence. So when you don't give a space in here, right? How does it even know that it has to read like I am a large language? So when you give space, I mean, for you, when you give a space, you can able to understand. When you don't give a space, even someone who's new to English can't know this is a I am a large language. So they can read in any different ways. I am a large language or any n number of ways, right? So it is only adhering to that particular model how it want to understand, right? Because it has been trained on certain set of data and certain format of data. It need not to be like a large language exactly. It can be large language, so it can be closest to the next probable sequence of token.
So yeah, maybe can you try encyclopedia once? Any big word? Like I'm just since you're talking about the space, I thought we'll take. Yeah. So here again, it's breaking, right? So like that's the intent I was asking. Like
Yeah, that answers the question, right?
yeah. Okay. Yeah. Got it. Yeah. Yes. Yeah.
Okay. Yeah, I think there was one more hand raised. Yes, Binabinu.
Hey, hi, Harish.
Yes,
Yeah,
hi.
okay. I just want to know the tokenization, how different is it between the old NLP and the tokenization happening in this LLM?
Honestly, I don't know. Anyone would like to answer that question?
If I'm correct, I might not. I have to refer it back, but it hasn't changed much. The word to vector hasn't changed much. What has changed is the corpus of data. The number of words that we have fed into the model has exponentially increased, if I may. Like we have been doing billions of tokens right now. So what happens when you do that is your corpus of words increases, which means the numbers you're dealing with also increases, which is why these models cannot run in your local system. It needs GPU because you will run out of your floating point system altogether. So the algorithm of splitting the words or splitting the letters didn't change much, but the amount of data that we are dealing with, the numbers that we are dealing with, has increased exponentially.
Okay, yeah, that answers a bit. But I'm also curious to know what is the real differences and how it is differed in LLM.
Maybe we will have one more session on deep diving into these nitty-gritty concepts of LLM. But this one is still on agents, so we will defer that
Okay,
question for a different event altogether.
okay, thank you.
Yeah, probably my question is also related to that. So then yeah, I'll I'll not ask the question.
Please go ahead. It will help us prepare.
Oh, sure. I was wondering, is there any protocol or is there any framework for this tokenization which all large language models use, or is it different from a model to model?
It actually differs from model to model. Um, I'm not sure like how it actually arrives at. Like this is how the tokenization should be defined in a particular model, though. But it differs from model to model, that is for sure. But I'm not sure like how that tokenization actually is differing. When you talk about like exact data points on that, when I'm not sure on that.
I can highly encourage everybody to go and look at word to vector algorithms. That's what it's called. And under word to vector problem, there are variety of algorithms. There are algorithms for, every letter, every character wise algorithms, word wise algorithms, sentence wise, document wise, all of this. And this is not just used in machine learning. This is also used in your search algorithms. So these are called word to vector problems. Go back, search about it. And in our deep dive session, we will go deeper into all these algorithms, how they work.
At which stage does it change the words to their root word? Couldn't understand that better. Maybe Aarti, can you explain the question a little?
So when you change a word to a vector, it needs to be converted into a root word so that the machine can actually understand, right? So it happens in NLP, but how does it happen in an LLM model?
The root word instead again in back to text from the numbers.
No.
No, for example, if you take a word like walking, it needs to be changed to walk so it can understand the meaning of the word and can give a number as a reference, right? So is that the same thing that happens for LLM also? That's what I was about to ask.
Yeah, I mean, like, exactly. We have like different types of encoding, like byte-pair encoding or different ways, right? So it is the same with LLM also.
I think even I don't know answer to that, but root word is more like your document cleanup. Some model does it, some model doesn't. We don't know whether GPT does it or not, or for any large language model for that matter. In our traditional algorithms, we create the vector space, so we have control over which words we pick and at which level, like whether we preserve walking or not. It's up to the model designer to decide. I have no information about that. Again, these are now I see more curiosity again how it is working internally and all that, but this session is not that. So let's just keep the questions to just that. And I'm going to refer all the deep learning questions for a different session. You can still ask it. I'm going to just keep a note of that and move it to a different session so that we can do agents and see some live action today.
I think we got the source code of it, Abhishek. Okay, yeah. That's it. Thanks. Thanks for having me. Thank you. Okay, cool. So continuing with this. So this is all about like a bit on tokens. And I don't know much of the difference between NLP tokens, LLM tokenizations, and even different models, how they are tokenizations, and deep into like different types of encodings or techniques, how this tokenization happens. I know that there are certain tokenization techniques, but again, it depends upon like how that encoding actually is. So that and the decoder, how that particular model has been defined and how it has been created, right? So all the tokenization techniques depends upon them. So that's why it's different from different LLM models. And how different it is from NLP to LLM, yeah, maybe we can deep dive into the later at a later point of time. Okay. I'll also research into it. Yeah, thank you. With that being said, I'll come back to this. How are you doing, right? So whenever you give a text to now again setting the context back. So we have GPT. GPT is nothing but your decoder only models. That is nothing but your, let's say, GPT. Okay. So now you give an input prompt to it. How are you doing? Right. So it should return something like I am fine, I'm doing fine, something like that, right? So how does it create that output? Yes. So the entire chunk of data, the entire data, how are you doing, gets into the decoder model. In the decoder model, it converts it into tokens. Tokens are nothing but your word representation of, number representation of your tokens. And that number, there is a heat map altogether, which helps you to preserve the contextual meaning of the data that has been pre-trained on. So it tries to identify, okay, how are you doing in that particular data that it has altogether. Then it tries to get the next probable token or the number in the weighted graph or in your attention graph, and meaning that the next probable word would be like, so how are you doing? The next output, the next text that it would generate is, for our sake, we'll just convert this, tokens into words just to understanding purposes. So the next probable word that it would generate is I. Okay. Now what it does is this auto regression. It combines all these words all together, meaning how are you doing? I. Okay. So this entire word, how are you doing again? I goes back into this decoder. So it is like, okay, the next immediate word, I'll able to find it. The next probable immediate word, I'll able to find it now. The next thing is, after how are you doing comes into the picture, the next word would be am. I am. So it tries to identify the next probable word in the sequence. That is nothing but your auto regression. So it takes in the previous previous output altogether, gives back to the decoder itself, and tries to find the next probable token or word in the sequence that it can generate. And this is where the auto regression comes into the picture. And I think that answers the question on the encoder. What happens to the output that is being generated? Like, how does it generate the output, right? So this output that is generated, Romeo and Juliet, for example, this sequence, right? Romeo and Juliet is a tragedy. This entire Romeo and Juliet is a tragedy goes back to the decoder, goes into the decoder. Then internally it identifies the next probable word that can generate in this particular sentence is return. So this again preserves the contextual meaning to the entire text that you are inputting. So that is the reason why the entire input is going to the decoder model altogether. Then again, the next probable sequence would be by William. that is how it is able to identify the next probable word after William in this context is Shakespeare, and not Johnson or anyone else. Yeah. So that is around the
Quick
point.
question.
Yes.
Uh,
Sure.
so how does the decoder know when it has to stop? How does it make sense that to the decoder that okay, sentence has been completed, something like that?
Got it. So, yeah. William Shakespeare. So it could have been completed after William Shakespeare altogether, right? But it tries to identify that if there any other probable word, like when you give, it is actually completely numbered, right? So it goes to the number, it uses the number and sees if there is any next immediate probable number that is within the heat map. There is no it has something called as an end of sequence. Okay, so something what you usually use like new line character or anything. So it defines the end of sequence within itself. So that is something which is internal to the model yet again. So it can identify that this is the end of the sequence of the words that it's auto-generating. So yet again, this might sometimes be a problem to the model altogether, and this is where the context window for a model comes into the picture also. So it can try to generate much more words, but it will stop at the context window that is defined for the particular model altogether. Okay, so where it ends is it when it's able to identify that end of sequence. Where it does not end is it tries to complete the end, generate text altogether, and it will end at the context window end altogether. But this might not answer your question completely because this is something high level even I can understand, but there's something much more to it, like on when to stop and when not to stop.
So Maurice, just trying to add on top of what Rahim said, right? So does it all relate to the prompt being asked? You ask more specific prompts and it knows where to stop, and you ask uh, more not like you just put like if it's not very specific and it tries to answer more and more stuff. If you just give Romeo and Juliet, it can talk so many things about it. So it tries to bring whatever is relative to it into the picture. And maybe if you start who wrote it, maybe it'll stop with William Shakespeare. Is that how, or like?
Yeah, similar to that, exactly. So when you just ask like who wrote William Shakespeare, who wrote Romeo and Juliet, so it will just give William Shakespeare wrote it. But
Correct.
this again depends upon like how you have the model attributes also. So there is something called as temperature comes into the picture now. So where you can make the model to be more creative altogether. When you just ask a question, it will not just answer your question. It will also try to give much more context to it that might not or might be or might not be relevant to your input prompt altogether.
Okay.
Yeah, so there are a lot of things
So
attached to it. So
it
it
could
can
be
be
one
like,
of the factor, but it has many other factors also.
exactly.
Okay.
Yeah, there are different ways to stop this context altogether. Sometimes it's an internal model logic itself that can appear, or you can interfere at any point of time. You can code your way into it, like whenever some maximum length or whenever this particular context has been exceeded, so stop the entire sequence. Or we have like there are a lot of attributes to it. Yes, this is one of the factors that can appear within the internal model logic, but there are a number of ways to know, like to make the LLM also stop. Uh, does that make sense? Little
Yeah.
bit.
Thank you.
Okay. Cool. So in order to understand this much more better, right? There is I added a reference in here. Maybe you can go through this reference altogether. So Daniel Warfield, so he's a very good blog writer. I actually look into a lot of blogs from him on all LLM and AI stuff altogether. So yeah, there is a lot many visual representations that you can go into to understand your encoder decoder part of it and what happens internal of an LLM. Right. Okay. So that being said, we'll move to the next one. We have talked more on large language model and what it does. And in this sessions or anywhere, we'll only talk about like pre-trained models altogether. That is only decoder models altogether. We'll not focus on the encoder only models or encoder decoder models. So we'll only focus on decoder only models. It's nothing but all your chat GPT, your not even perplexity, I'll not talk about perplexity, but your Gemini and any other chat-based your GPT models, right? So all these models are nothing but your decoder only models or decoder only transformers altogether. Okay, so now talking about this LLM, there are few limitations to this LLM or few shortcomings of this LLM. Okay, so we'll deep dive into the shortcomings of this LLM so that we can understand the birthplace of an agentic approach. Okay. Yeah. So, so the first limitation that I can think of when you input something to a LLM is hallucination. So many was about hallucination, then fine tuning, then RAG. A lot of things came into the picture, right? So we'll talk a little about hallucinations for now. Okay. So what is nothing but a hallucination in LLM word is? So you give an input to an LLM. LLM starts giving out a response in a more creative manner that sounds like something is real, but it is actually not. So that is nothing but an hallucination. So all the definitions that I've written in here starts generating words in the direction of incorrect information. That is, when you start writing something like Romeo and Juliet is a tragedy written by William, let's say instead of Shakespeare, it gives us Johnson. And then it again tries to, the next probable set of tokens, right? It tries to justify your previously set tokens. Okay. So it tries to complete the entire sequence of words in a way that it gives the right answer to you, but it actually an incorrect information that is giving in the output. Okay, so that is nothing but hallucinations. Okay. So a small example is when you ask a kid, right? So you ask a kid who has been just trained on addition. You ask a kid to what is 4 plus 4 or what is 4 plus 2? Okay, the kid answers us 8 instead of 6. Now the problem is you don't know what the actual thought process of the kid. The kid might have confused addition with multiplication, and I would have told you the answer as 8. Right now, this is where the hallucination comes in. So you know that it is an incorrect information, but you don't know how that incorrect information has been arrived. So is it because the model has been trained on some false information, or the model is the next probable set of sequence of tokens, right? So it is not able to identify that next sequence of tokens correctly. Okay, so it might be like any number of things, right? So what you do now to the kid in order to solve this problem is you don't give the answer straightly as addition is when you have like 4, then you have to 1, 2. You don't tell the kid now. So what you ask the kid is, how do you say that the answer is 8? So can you give me the reason for it? The kid who has just been understanding like what is addition will put out the hands, says 1, 2, 3, 4, 5, 6. Now again, there is a high probable chance, since we have asked the kid to think through the thought process on how it arrived at the answer, there's a high probable chance now the kid would spit the right answer as 6 and not 8. But there is still a chance where the kid would say 8. But here the thing is, there's a high probability that the answer that it spit out would be the right answer instead of the incorrect information that it gave out. Okay, So this is where whenever right now in ChatGPT, when you ask something, right? So it goes into the mode as like reasoning. It shows something as reasoning, right? So it's nothing but it internally creates all these tokens. So Romeo is a tragedy written. When I say Romeo is a tragedy written, and I've enabled the reasoning into it. Now the reasoning goes like the next probable set of tokens. Okay, the user is asking me about Romeo and Juliet. So what is Romeo and Juliet? So it tries to internally answer itself before spitting the final answer for you. Okay, these are again tokens. So in ChatGPT, if you just now go and ask like DeepSeek does it better for me. This thinking mode. So it internally tries to answer, okay, I need to explain why Romeo and is a tragedy. So it tries to reason out the question that you have said it earlier before spitting its final response. Okay, in this way, and this concept altogether is nothing but called as chain of thought prompting. Okay, so you enable the LLM itself to reason out the steps on the thought process before arriving at the final response. So I asked the model. So before I asked what is 4 plus 2, split out the answer as 8. Now we ask the kid again, what is the 4 plus 2? Reason out the steps. Now the kid thinks of. So you have to perform addition, start with the number 4, add 2 to it. Now 4 plus 2 is 6. Now it spits out the right answer. So this is one of the shortcomings of LLM, and which is hallucination. This is one way to solve this hallucination. Right? So if it again spits out the answer as 8, that means that it would have been trained on a different, false information, or we have to give on different prompting techniques altogether in order to arrive at the right answer. So this is the first limitation of a shortcoming of an LLM model. Okay. I think all the questions in the chat has been answered. Thank you, Bhavani, for that. Yeah. Moving on to the next shortcoming, right, of an LLM. Now, all you saw on the LLM model, right? So, on the decoder only models. So, you have been pre-trained on few data. So, if there is any new data that you want, that you are giving in, and you want some answers from a new set of data, right? So, you can't do that, as well as you can't interact with the real world. So, when I ask, like, what is the classic example, wherever you go, in this is what is the weather today? So LLM can't answer you that, can't give you the answer to that. So this is where you have to have a real world interaction comes into the picture. Okay. So when I ask a question without any real world interaction to a model, the model gives me the answer as this. So what are the trending stocks today in Indian stock market? Now the crash coming into the picture. So like stock market crash came in, and so I wanted to identify what is the stocks that is performing well for today. So now it is not having that particular information because it is pre-trained on certain set of data. So it gives me the responses. It is unable to access real-time stock market data. Okay. So this is one of the other shortcoming of LLM. Okay. So how can we solve this shortcoming? Is something called as function calling or tool calling, or giving an external knowledge base attached to it. Okay, so function calling is nothing but, let's say, this stocks, right, I can have some kind of an API, external API. So I need to call this external API in order to get that information. Okay, so now let's say that I have attached a particular API into the model, and when I say into the model, there's nothing but into the context of the model. So what are the trending stocks today in the Indian market? Now, after attaching this function to it, or the knowledge base or the tool to it, in order to get the particular answer, we need to interact with the real world. That is called as the endpoint. Get the needed information, or we can always say like search the web. Search the web is a classic example of a function calling. So you are able to, even when you did this chat GPT, right, you saw something else like search enable. So this search enable is, it would help you to search the entire web. That is nothing but like a Google search that you do. It then gets the answer from series of different websites and collates it for you and gives it in the response. So this is a classic example of a function calling search the web. Okay. So when I enable search the web, it is able to search the web for the trending stocks today, and it is able to give the result for me too. Yeah. So these are the main two limitations of an LLM model. Okay. So coming on to the third one. Before that, any questions or anything to share?
Just one question on the chat.
Okay.
Trending stocks, it sees the stocks that's currently there. How does it do for weather?
Which year had the best weather in Chennai? Can we ask that question and see?
Of course.
So enable search the web also. So it's able to, it knows that I don't have the answer for it. So it goes into the search that it uses some external tools in order to pull all the results. And again, it goes into the reasoning steps, thought process altogether before spitting out the final response and gives you the answer for it. Does that answer your question? Yes, perfect. Yes, Aditya.
Yeah. So when we say a model is a reasoning model or it could reason, but during training we just encode the data, right? Like so, at what part do they classify a model as reasoning model? Are there any instructions that are provided to the model, or like are the instructions are on top of a existing pre-trained model? Like how does reasoning work there?
Can you repeat that question?
Yeah, sure.
Again?
So I meant if all the models are trained with similar data, or like large volumes of data, when we classify a model as a reasoning model, is the reasoning a set of instructions that are provided to the model post like training, or like during training itself they would let the model be like a like because when we just said it is encoding and decoding, like the reasoning and in between part, like I think it would be after
Got it.
decoding, but so where does the reasoning part come in the model?
Yeah, I do not want to much confuse on that, but there is something called as reinforcement learning, on which the DeepSeek models are completely being trained on, where it helps you to intuitively reason out by itself altogether. But let's, for this context, let's stick with the way that um, um, even though it's not a reasoning model altogether implicitly, we are making the model a reasoning model by asking it to reason out the entire, reason out the steps before spitting the final answer. So to answer the question, how the model is termed as a reasoning model is during the training process, where it has an implicit learning capability that we can inject into it.
Okay.
But yeah, I do not want to go
Sure.
further much into it.
Sure, fair enough.
Yeah, so I had asked one question, which is so if it's a simple question. Maybe it's related to context window, but like you can confirm that. So if I ask Claude something that like I want some ideas on this thing, and it just not answers that, it actually starts making that thing. But I just want to know the path to follow, right? So is that related to the context window?
I couldn't get you. Sorry.
Say like if I want to make a weather prediction app, and I'm asking it that can you give me ideas like how to design this, how to architect this thing, and it starts making that right away. It gives me a path, but it also starts making it right away. But I don't want it to like make that thing, right? I just want a follow. So is that related to context window?
No, it is actually related to your prompting technique. If you don't want it, you have to explicitly say to the model, so it does not give you that. It has no relation to the context window altogether.
Okay.
Am I on are we on the right page on the question, the answer? Because
Yeah.
okay.
Yeah, because like I have faced it, like even when I prompt it with, just give me a roadmap to this and don't try like making it out. It still tries to make that thing. So yeah.
There are two aspects to it. One is your prompting technique, and the other one is how that model, like the tool calling details that it has been provided, right? So it would have been in such a way that even if, like whatever it is, just call this tool. If it finds some keywords into it, then it starts auto generating the code for you, even if you explicitly say tell it to the LLM, because this particular context that code or give me the write the application for a certain set of when it has a certain set of keywords, right? So that particular context or generate the code would have been pre-trained or given to the LLM altogether. So even if you externally specify that do not give me such things, the LLM does it because it has been pre-programmed to do it. It is not the LLM who does it. It's the wrapper on which, that is between your text and your model. They have written a wrapper. That particular wrapper is where these stuffs happen. Like it automatically generates or it listens to your input and then acts according to it. But when you ask the model directly, that don't generate it, when you model directly without any other to Claude or anything, which is a wrapper to the model, just to the model directly using any other like local models, have a local model and try to use a text interface to it. So when you explicitly say it, it will not give you the code or the application by itself, just the roadmap for you.
Okay, so it's the wrappers doing.
Yes, exactly.
Cool. Got it.
Yeah.
Thank you.
Perfect. The wrapper, how it does it, maybe I will give you an example. When we go to the designing agent, I'll give you that an example of it. How does it know that this particular tool has to be called, or whether I have to give this output or not, whether I have to just give me the roadmap or whether I have to give the entire application. So when you say create a project, so it might be looking into just create a project, but now and ignore the other request that is given from the getting from the user and creates the entire project for you. That might also be happening, but again, depends upon the wrapper. Yeah, we'll come to that. Sure.
Cool. Thank you.
Okay. So moving on.
Keeping the
Good
time
evening.
constraint in mind, we might ask participants to put all your questions on the chat, and then Maurice can answer it at the end, so that we can finish the presentation and go to Q&A and then start building stuff, because I want all of us to get hands-on. I know we love to, listen, but we want to get hands-on too. So all the questions on the chat, and at the end, we will answer everything for sure.
Perfect. Okay. Can everyone give us a thumbs up? I'll know how many of you are sleeping or how many of you are listening. Perfect. Hey, I see a lot many hands. Cool. Thank you. Thanks, everyone. Yeah. Coming back to the context of it. So there's only the last practical shortcoming that I can think of in order to drive it in a way to the direction of an AI agent is iterative reasoning. Okay. That is, when you ask a model some question, right? It's able to give you a thought process altogether, chain of thought prompting. Again, it's a chain altogether. But after giving your final response to you, does it really go back and check the response that I have given is the correct response or not? That is iteratively going through your reasoning process, your answer, and then taking the entire thing yet again into the context and checks against itself whether what I have given is the final result, or do I have to add anything to it? That is nothing but your iterative reasoning. So multiple reasoning steps. Doesn't do that. No, does not do that. LLM does not do it by default. So when you ask these some of the steps, just gives you this. You have to perform addition. 4 + 2 is equal to 6. Thus the answer is 6. Ends there, right? Altogether. But still, this answer, whether it's right or wrong, whether I have to stop at it, this evaluation, right? So the LLM does not do it by itself. So that is one of the other shortcomings of an iterative reasoning. So how to solve that is where your wrapper comes into the picture. Your wrapper is nothing but your LLM application on top of your model. So whenever you give an input, right? So this is an example for you. So a company wants to improve customer satisfaction. So what I have to do next? So it immediately tries to reason, but it immediately sends you a response stating that you should measure the impact of your changes to see if satisfaction improves. So that is the response that it gives. But all the entire roadmap of it, right? It is not able to give because the answer that it gave out, it does not reason out this particular answer yet again in order to arrive at the actual final response that is fine-tuned, even like giving a niche response to your question. So how to do that is you have to create workflows. This is where your LLM application development comes into the picture. So this is where the wrapper between your input and your model comes into the picture. Now your workflow is nothing but controlling your entire input to the model that you are giving. So you give the input to the model, then the model tries to reason and give a response to that. Then you again give to the model asking whether is this a final response or is it the correct answer that I wanted to achieve? Then it again tries to reason out the steps altogether and gives us a final response completely. So I just given an example. This might not be the best example though, but you could see like in here, I wanted to improve the customer satisfaction, want the immediate next step to be performed. Okay, so it goes to a series of iterative reasoning, that is series of reasoning steps altogether. Then at the end, it identifies the next immediate step is I have to analyze the data first. Without analyzing data, you won't get the answer to it, right? So this is where the workflows that stands between your model and your text comes into the picture that helps you to achieve this iterative reasoning in order to still fine-tune your response in a way that it gives out the correct response that you want. That is the immediate complete roadmap in this context. So yes, these are the complete limitations and the solutions for these limitations of an LLM. So when I say that this may not be the entire set of limitations, but I wanted to drive it in a way that what is the need for an AI agent. So all these things, right? Your chain of thought prompting, your function calling, your iterative reasoning, right? So all these paved with a way for something called as a React framework. And we're still not going into agents. That's one small thing that I wanted to share because this is exactly what agent is. So there's something called as React framework. So all these limitations paved the way for these creation of this particular compelling framework called React. And this React is not your React.js for UI, but it's something called as reasoning and taking action. So all these steps, right? Whatever you saw, the limitations and the solutions, you saw it separately. What if you combine all of them all together? So you create an application in a way that you make the LLM to reason out the steps, then you take the action on the steps. So let's say, for an example, you have asked what is the weather today, right? How does it know that it has to go to the particular web search when you ask what is the weather today? Okay. This is where your LLM reasoning comes into the picture. So it tries to create sequence of steps. So reasoning, action, and observation. So these are the 3 steps. So now all your chain of thought prompting and everything is unstructured right now. Okay. This React framework helps you to structurize this chain of thought prompting and reasoning all and tool calling or function calling or connecting to an external knowledge base or searching the web. So how do I structure this? So this is where the React framework comes into the picture, which structures all these solutions for you. So one is reasoning. First step is then action plan. reasoning. Reasoning is where you create your action plan. Then observation. So in reasoning, what you do is when you ask like what is the weather today, so it reasons out the steps. Okay, user is asking me the weather for today. I do not have the information for today's weather. What do I have? Okay, so now is where your it creates an action plan for you, right? So what is the weather today? It gives you the answer like I want to check on today's weather. I need to search the web for the information. So this is the action plan that it can create for you. Now the action is searching the web and giving, searching the web for you. Observation is after searching the web, it gives you all the information, all the details to you, right? So collating all the details and giving it back to the model. So this is where the iterative reasoning also comes into the picture. After observation, now you're giving it back to the model to reason on the steps again altogether to check whether I have arrived with the answer or whether is there any other action plan that I have to perform altogether. Whether I have to search the web again for another answer or whether I have to use another tool in order to find the next step of answer, right? Next step of result. Okay. So that reasoning, again, it does it. So this React framework helps you to do COT, that is chain of thought prompting, do iterative reasoning, and also make function calling altogether, which the LLM by default does not do, but this React framework will help you to do it in a structured way. So it creates three structures, which is reason, action, observation. Then again, after observation, it again goes back to the observation, entire observation goes back to the model as an input prompt altogether. Then again, all the three steps happen. Reasoning. Okay. Reasoning, then it tries to arrive at the final answer altogether. Okay. If the answer is found, then it stops over there. Then the action observation does not come into the picture. Sure. Okay. So this is where the example is. So you can still, there is an entire website to it, React, and the paper completely all together. So you can go through to it in order to understand this much more better. But here is a small diagram for you. So LLM, actions with an external environment, might be an API call searching the web. Observations goes back to the LLM model altogether. This is where. So your reason only and act only combine into together. LLM does all this for you. Now your AI agents. In one line to complete what agent is, when you put this React style framework into action, that is nothing but your agent altogether. All your LLM applications are not agents, but it is something, it is an application yet again, it is software application. When it autonomously help you to derive the final answer powered by an LLM altogether. This is called agent altogether. Okay, so agents are nothing but putting your React framework into action for you. And this is where an excellent blog comes into the picture on Anthropic, where they explain what agents are and what workflows are. So in order to, again, define it better, you can go through this particular reference on building effective agents. And this is the picture I took from there, though. So it helps you to, whenever you make an call to the LLM. So LLM does the action for you using any other external tools, getting the feedback or the observation. Again, LLM checks it and checks whether it has to stop at the answer or whether it has to perform the action again. So this is nothing but your agentic framework. And instead of an environment, you put an external knowledge base directly into it. Instead of an API call, just a vector database into it. It becomes your agentic RAG altogether. So you understand much more better on agents and agentic RAG approaches altogether. Yeah. So this is on the theory part of it. Now, can we have a pretty much hands-on on creating an AI agent? I'll paste the link in the chat. I hope everyone was able to open this out. Yeah. Make a copy in your drive itself altogether, and then you can make changes or anything to it. Perfect. So I'll not, due to the time constraint, I'll not, I thought I can code it all together for you. But due to the time constraint, let's not get into agent development, but I'll give you a glimpse of what AI agents are with this example in action. Okay. And then we'll move completely to MCP. I think MCP is where everyone is excited about. Hey, I'll just walk you through this example altogether. So we'll be using LangChain for this example. The first thing is this. So I'll not. This is just some installing dependencies. People using Python would be aware of it, and this exclamation is nothing but letting you know that it's a bash script in Collabs, not a Python code. Uh, Let it complete. In order to run in your local machine, you need to have Gemini API key, which you can get from Google AI Studio. It's pretty much simple. You can Google it and get that. And where you have to put it is in your notebook access. The name as Google API key. Put your API key in here so that you can run the model altogether. Okay. Now the second snippet is to provide the configuration of the model that you are going to use. Okay, I'm going to use Gemini 2.0 Flash for this model for this example. Once this is done, third one I'll come to it. Now what you've given is you have defined the LLM model altogether. Now LangChain has a predefined way of creating a React style agent. So the naming convention itself, it's a create React agent. Okay. So that is what the LangChain also has. So this particular snippet of code helps you to create the agent for you. Here, it says that tools is not defined. So the input to that particular agent are nothing but LLM, your tools, and memory. I'll not deep dive into this memory, but this is nothing but like when you ask multiple questions. So one question is done, then you ask one more prompt. It has to have the memory of the previous context altogether. So this is where like memory comes into the picture. So I'll not deep dive into this memory, but this is something which is needed for your React style agent to perform. But in here, I'm giving this particular tool. In this tool, I have given a basic written A plus B for add, multiply, and divide. And you could see something called as here I have given comments, this is in Python, it's called docstring. And when you define a tool altogether, and this is where you tell the model on when to use this tool. Okay, so in your model, before giving the input, this LangChain automatically gives this entire doc string into the model's context altogether. It sets the model's context. So then model, if you ask a question like add 3 plus 4, then it goes into this. We have provided the external context to it, right? It knows that I have to call this particular tool because this tool is something but adding of 2 numbers. Okay. So this is how the model can understand whether to call a tool to perform an action or whether not to call a tool to perform an action altogether. So this is why it's important to provide doc strings or a description of your method. Okay. So now you have defined a tool altogether, and now you are creating an agent. Okay. So how does this agent looks like? What is the this particular agent is? Okay. So this is what happens. You give an input, this particular agent, which has the LLM defined into it, will reason out the details and checks whether it has to call the tools. Then it call the tool, get the observation, again reason out the steps for you based on the observation that has been generated by the tool calling or the function calling or the knowledge base that you have injected into it. checks whether I have the final answer or not, using the LLM itself for evaluation, and then again call the tool if needed, else it ends the entire thing. So this way is right. This is nothing but a workflow for you. So in just all agents are workflows, but all workflows are not agents. So two things to note on agents. Agents is when you put your React framework into action, and all agents are workflows, but not all workflows are agents. So that is all about actual AI agents. Okay, now let's put this AI agent into action. So what I'm giving is, I'm asking the question, add 3 plus 4. I'll remove this magic number. Just say add 3 plus 4. Okay, and run this. Okay, and I pretty print this, so it is easy to understand. So the human messages add 3 and 4. AI message is nothing but the reasoning that the model does it by itself. So this is pretty printed in a way. This is not the exact thing, but in here you could see we are doing a tool calling to this particular add function. Okay, and the arguments that are being given is 3, 4, and as a result from that, the tool result is 7. And then again, AI message kicks in. Internally, it reasons out this particular answer as 7. Whether this has the final answer or not, it has the final answer. So it is spitting out the final response stating that sum of 3 and 4 is 7. So this is exactly the way when you inject some, enable the web search to this particular LLM, right? To this particular agent. That's instead of a normal divide function, just say search the web, and you write the code for how to search the web, right? So then it does the web search for you. So this is where that wrapper lies in between your text interface and your model, which currently ChatGPT, Claude, or DeepSeek or anything does it for you. Okay. And this is completely agents for you. And in order to build this workflow altogether, I told like agent is a workflow, right? So I've written a code. This is again inspired from LangChain altogether. So this is where like how to define that entire workflow. You create a nodes altogether, all these things, right? So instead of just calling this recreate React agent, in this example, you can see how to create the agent itself from scratch, how to create this workflow, LLM called action environment. So this is pre-built. This is something that you can build on your own. And this is again reference from LangChain community. So I hope you had a better understanding what agents are, what workflows are, and what LLM applications are right now. So when you just use an API key, it's an LLM application. When you define this particular reasoning React framework altogether, it's an AI agent, and your workflow enables you to create this AI agent for you to create this entire React-based framework. So when you see in here, at the rate of tool decorator. So when I defined it over there, so this is where I provide this LLM that this is a tool. Use this, inject this into your context altogether. And which tool it should call, it again depends on the LLM itself. LLM has to arrive at like which tool it should call based on the reasoning that it is creating. And in order to enable this tool has to be called, this is where the context of this particular tool comes into the picture. We provide it in the description of this particular tool. If we provide the description of this tool, the reasoning will take this particular description into its context and arrive at an answer, meaning arrive at a reason that whether it has to call this tool or not.
So tool is nothing but a function.
Correct. Yes, both are the same. Tools, functions, call. Wait, Shankar, how setting up an agent different from setting up an API calls with Zapier for a workflow? Is the difference just that we are using LLM APIs? Yes. So in API calls with Zapier for a workflow, you provide conditions to it, right? Now in here, you're not providing any if conditions to it. If add, then do this. But you're just giving it an entire text format, and LLM itself identifies whether which tool it has to call altogether. So it is not an if condition. Now it's reasoning comes into the picture for you, and that's the difference between your API integration with Zapier workflow and AI agents altogether.
I think there is one more nuance to it called agentic workflows, and that's what Zapier and N8N are trying to achieve, where you have series of workflows working hand in hand with each other. That's called agentic workflows, not just one agent doing a workflow, multiple things. And that's the difference in using something like Zapier. The session that we are doing today, you can expand it as big as writing your own Zapier, writing your own agents on top of it, and then having these two agents talk together. All of that you can do with what you have seen in LangChain itself.
It's pretty much it. There's one more question. So before executing every task, does the agent scans for all the tools and its capabilities every time? It does not scans for all the tools, because that is where I'm configuring this entire tool into the context. Whenever I'm creating an agent, let me share the screen again. Just this example alone. So I've defined the tools in here and configured while creating an agent. So all your details regarding this tools, right, is already configured in your agent. It does not scans for the tools every single time, but it has the knowledge base. Now your pre-trained data, right? Now we have much more extended context to it. If it is an add A and B thing comes into the picture, then it has to call this particular function. So not every single time it scans for the tools, but the details are already provided. It just needs to figure out whether I have to call this tool or not. And the scanning of all the tools happens prior during configuration.
I think what makes something an agentic workflow versus a normal workflow is who makes the action, right? If you're doing an UI-based application, the intent is very strong as to who is making the action. The user is making the action. In this case, the user is being very vague as to what is the best weather in Chennai in last 10 years. User is being vague, but also very precise in our language, because we understand language, it's very precise for us, but for a long language model, it's not. And that's where agent kicks in, unlike traditional workflows. In here, we think we have a lot of context, but because our brain is trained that way, but the system doesn't, which is when it needs an external system to do the answer. If you actually design these tools for your workflows, then you will understand how much it doesn't understand, how much it pisses you off. So that's where the handoff is between a traditional workflow where you give it a lot of context. Even JSON has a lot of context for a system as compared to a human being. So that is a very subtle difference. When you're working with a UI, the system actually has a lot more context than you. When you're working with language, you have a lot of context over the system. So it's a nice segue between finding the middle between you and the system. And that's still evolving. Okay. So that was a wonderful session, isn't it, Maurice? We touched every little corner of LLM, who all enjoyed